Okay, and welcome back. Let's go through finally part three. Now, this is a diverging lens in this case, so we got to be a little bit careful. And this most people have the most difficulty with the diverging lenses and mirrors, but we just have to remember that their focal points are on the opposite side because it diverges, so we have to look backwards. So that's the key. If you can understand that we just always focus on the opposite focal point than what we do on a converging, will be fine. So first we need focal points. So let me add those on here. So let's say 1, 2, 3, 4. Let's just call that 1, 2, 3, 4. And the center of curvature as for a diverging lens, it actually isn't very important. And then also we need an object, and the location of the object doesn't really matter, as you'll see for a diverging as well. We get pretty much the same type of image no matter where we put it relative to the diverging lens. So let's put something like that. Actually, that's a little bit, I don't need it that big. Let's make it a little smaller. So let's put an object there. So let's follow our rules first of all, but stay with me here because you got to be really, really careful. Let's start with the easiest one of all, and that's rule number 2. Oh, never leave this rule out because it's the easiest one. So we start at the object, and then we just go straight through the center of the lens. So there's rule number 1. Nothing changes there. It's when we deal with the focal points that the rules are kind of backwards, so be careful. So rule number 1, we'll go back to the first one, is if I go parallel to the principal axis. So normally, right, in a converging lens, the ray then would go through the focal point. But rays don't converge, they diverge. So they actually, I better do this a little more accurately. So they actually, I want to trace this backwards because this ray, when it passes through, it's diverging so that it traces backwards through the focal point, right? So there's my ray. It's a diverging ray. You see how the two rays are diverging? Well, how do you know where to draw this ray right here, the second one? It has to trace backwards through F. So it still follows the rule, right? Parallel ray through F, but it's got a negative focal point, so you have to make sure it goes backwards through the focal point on the left side of the lens. Rule number 3 is going to be exactly the same. If I go through F and then emerging or sorry, diverging on the other side, normally we go through F on this side and then parallel, but wait, that wouldn't look right because it would be converging. We have to line up our ray with the focal point on the other side, back it up, and then my ray comes through parallel. So those are my 3 rays. I followed the rules. Rule 1, parallel ray through the lens diverges so that it traces backwards. Ray 2, straight through the lens without doing anything, easy. And then ray 3, through the focal point, but I'm aiming for the other focal point over here. Now, how do I find the image? Well, this is kind of a cool part. It's a virtual image, so if my eyeball was over here, what would I actually be seeing? My eye would be tracing these 3 rays backwards to where it thinks they come from. So I line my straight edge up. I'm going to use a dotted line. So if I line my straight edge up with these and I trace them backwards, then I can see, and then this one should be a dotted line too because it's bouncing backwards. Then I get my image right there. Look, it's got some slightly different properties. This time it's upright. Little rule of thumb, upright images are never, ever real. So in this case, it's virtual. Anytime you have to trace rays backwards to where you think they came from, that's what a virtual image is. It is reduced. Images produced by diverging lenses and mirrors are always smaller. They're never bigger. And it should be always, always between F and the lens. Okay, so you can try. Now I want you to try the mirror one by yourself because we do the exact same rules. Remember, if it's a diverging mirror, aim for the opposite focal point than what you usually would. that's going to give you three diverging rays that you then have to trace backwards, and where they virtually came from is where that image is. It's a virtual image. Okay, last piece is we can also um, plug all this stuff in. There's a lens slash mirror equation, which if you know the measurements of these things, so again, let me go to one of my diagrams. So for example, I would call this distance, here's the object. So this distance from the vertical axis to the object would be DO, the object distance. And then this distance from the image to the mirror is called the image, sorry, not O, image, DI, image distance. I have this distance right here is the focal length. So if I know those three, or any combination of two of those three lengths, the distance from the object to the mirror, the distance from the image to the mirror or lens, and the distance of the focal point, the focal length, then I can plug and chug in what's called the lens or mirror equation, which says 1 over the focal length equals 1 over the image distance plus 1 over the object distance. The only thing that makes the lens mirror equation tricky to use is that you have to be very, very careful with the signs. The sign always has to refer to, for example, let's start with the image. Anytime the image is virtual, right, that means the DI is negative. So there's, in other words, there's a real side to the lens, the positive side of the lens or mirror, and then there's a negative side of the lens or mirror. The real side is where always where the light comes from. So DO, the object distance, there is such thing as a virtual object, by the way, because the object can be, if you're using a two-lens system, the image formed by one lens can be the object for the second lens, which makes it sometimes it can be a virtual object. But for our problems, we will always assume DO is always a positive value. The image then depends on what kind of image you get. If it's a mirror, if the image forms behind the mirror, then it's a negative distance. If the image forms in front of the mirror, like it should, that's a real image, it's a positive. For a lens, if the image forms behind the lens, that's where the light's supposed to go, through the lens and form an image, that's positive. If the image forms in front of the lens, that's a virtual image, that's a negative. And then F in this equation is very simple. Converging lenses and mirrors, right? Converging form more virtual, or sorry, more often than not real images. So we have positive focal lengths when it's a converging, negative focal lengths. Remember, we had to switch it and like go with the opposite focal point for the diverging lens and mirror. So if we put those three values into this equation, we can solve for, actually we put two of the three in, we can always solve for the missing piece. Sometimes AP exams ask you to draw the diagrams. Actually, they always ask you to draw a diagram. And then sometimes they ask you to calculate the location of the image or whatever. Um, Calculate doesn't always mean just measure your diagram. They want you to use the equation, which is actually pretty easy. Oh, and then lastly at the bottom, I can also learn a little bit more about the size of the object because that's always simply a ratio of the image to the object. So a magnification value of greater than 1 would mean that the image is greater than the object size, so it's a magnified image, versus a reduced image. If you get a positive value, then it tells you that it's upright or inverted. My advice always is don't rely on equations. You can knock out a quick little diagram. You can always easily have perfect proof whether something's bigger or smaller, or right side up or upside down. Plus, for the upside down or right side up, it's easy to remember. Real images are always inverted. Virtual images are always upright. Always, always, always. So I hope this helps you through your spring break assignments. Please don't hesitate to ask questions. Don't wait to the last minute. But again, the point here is that you learn it, not just do it, but to actually come back with a pretty good idea. We can clean things up a little bit in the week or so leading up to the exam, but this is something that I think you can really have some success with, and we can hope for a nice big 15-point question on ray diagrams, because I know everyone can do it. So again, ask questions if you need it. Start early so that you're not waiting until the last second. Don't come back on Monday and say I didn't get it. I know you can get this. start looking ahead at refraction and diffraction problems in the WebAssign because we only have one day to spend on that. Other than that, have a great break. See you in about a week.